Hey guys, today we're going to continue learning more about data types in Haskell. So last time I showed you the data keyword for constructing types in Haskell. Whenever we construct a type using this data keyword, we refer to these as algebraic data types. So just in case you hear this somewhere else, all you need to know about algebraic data types is that these are data types that are created using the data keyword in Haskell and not just the type keyword. So there's two parts of algebraic data types that we really need to take a good look at. So one is the data or type constructors. And really all this means is the type name you're giving your data. So the first thing you do when you write a new data type in Haskell using the data keyword is you give it a type name. So this is going to be the name that's used in your type signature. So like let's say you have a function sumfunc and it returns a type of your new data type. This is what you're going to put. This name, this first thing is what you're going to put as the type name. The second thing we should be aware of are the value constructors here. So a value constructor is going to make the values associated with your type. So let's say our type name data type here, our sample data type here, it has two value constructors, val1 and val2. So val1 creates a value all on its own. So if you just write val1, that's already a value. Val2, in order to construct a value, needs to have an int attached to it. So val2 only actually becomes a value on its own when you give it an int. So if you write like val2 5, or let's say you have some variable and you write val2 and you attach that variable to it. Now this val2 attached with the variable becomes a value. Just on its own, it's just a value constructor, which you could think of as being like a function that takes an int and returns a type name. Let's try out a more specific example of this. So let's say we're trying to create a data type that's going to keep track of different students. So we'll call it specifically student ID. So student ID is going to have two strings attached to it. Okay, and it's going to have, let's say, the first string will be your McMaster ID, MID. And the second string will be your student number. So we'll pattern match on both of these things to pull them out. Okay, so we've created a data type, student ID, and what we've done is we've made, this confuses a little some people at first, but we've made the value constructor, student ID here, the same thing as the type name. So it allows you to do this because whenever you write a student ID inside of a type signature, it knows that you're referring to the type name. Whereas if you write it in outside of a type signature, like let's say for pattern matching purposes, then it knows you must be referring to the value constructor student ID. Okay, so student ID is a value constructor that has two strings attached to it. So we can pattern match onto it and be like, well, the first string here, we'll write a function for it, mapID, that returns it. And now that we've written this function here, anybody reading this code can kind of figure out, okay, the first string that's attached to it, that must represent your McMaster ID. Whereas the second string, we've written a function studentNum that pattern matches and pulls out the student number. So now we know, okay, this second string that's attached to it, anybody reading this code could tell, well, we must be reserving that to represent the student number because of this function we wrote. Now, a shortcut, we often do this when we create data types that have value constructors with different types attached to it. We write these functions to pull those types out of the value constructors. So a shortcut we could have done for this, we could have written this a different way. So instead of writing it, so I'm going to comment all of this. And actually, I'll use a multi-line comment to do this. So the other way we could have written this is data student ID equals, and then we would write the value constructor name, and then we would put curly braces and we would put Mac ID string student num string. Okay, and this is actually, this right here is actually just a short form, a special syntax for all of this code right here. Okay, and this way we could look at this and be like, okay, we have this student, oh, and sorry, this should be student ID to be the same thing as what we wrote up here. We have this student ID value constructor, and it has two strings attached to it. And we can be specific about what we want these two strings to represent. We can be like, well, this string represents a Mac ID, and this string represents a student number. Okay, and these two things here will act as functions to pull out the student number and Mac ID respectively of the string. So let's make an example student here. Okay, Jimmy, and he has student number 0001. Okay, so we could save this and let's load it into GHCI. Okay, and what we could do, so remember, let's say we try and write student num, we get an error right now because it has no way of showing student one here, right? And we want to be able to show our data type, any data type that we create, we have to put this deriving show underneath. Make sure you save, go back, reload. Let's try that again. Okay, so now it can show, and it's saying this is student ID with Mac ID equal to Jimmy and student num equal to 0001. And let's say I say Mac ID, I use this as a function, student1. See, now it returns Jimmy. Similarly, if I do student num student1, sorry, student num student1, it returns the student number of this. So we can do, let's do one more example of this. Let's say we have a university ID. So let's get rid of this code now. Let's create a data type, university ID. And this data type is going to be a student ID with Mac ID, string, student num, string. Or, so this is going to be a more generalized form of what we were doing now. So instead of just having IDs for students, we're also going to have a faculty ID. And a faculty ID is going to have a Mac ID, string, a faculty num string, and a salary float. Okay? And now we can write a function over this type. Let's say a function det that takes a university ID and returns a float. And the way we could calculate the det, let's say if you're a student, regardless of who you are or what your student number is, you're in a bunch of det. Whereas if you are a faculty, let's just write faculty ID here. So we won't bother pattern matching on faculty ID, and we'll make sure to put it underneath student ID here. Okay, so that we know, well, if it makes it to this case here, it must be a faculty ID because student ID and faculty ID are the only two value constructors here. So just write a variable here, faculty ID is going to be equal to 2 times the salary of faculty ID. So we're writing salary, okay, the salary here, to pull out whatever the salary is attached to the faculty ID here. And we can make a few examples of this, some few test cases. So let's say we have student 1 is equal to student ID. Let's make the same student as before, Jimmy. 1. And then we'll have prof1 is going to be equal to, so we're going to have a Mac ID, a faculty num, and a salary. Faculty ID, so the Mac ID is going to be me, Curtis. Now we need a faculty num. And salary 2. Oh, and this isn't a string. This is a float. Okay. So let's save this and let's reload it. And we can try out det of student 1. Okay. It writes this in a short form, 1.e to the 12. So this e to the 12 means 1.0 times 10 to the power of 12. Okay, so it's this number. There must be 12 zeros here. Okay, this must be 12 zeros here. And let's see the det of prof1. Well, prof1's det is a lot better than the student's det. And you'll notice both of these things are university IDs, even though even though one is a student and one is a faculty, these are both under the same type. Okay, and that way we could have one function that takes both of these things as an argument. So last time I gave you an example of a recursive type for defining the natural numbers. So this was a type that used itself inside of its own definition. And we needed this type to be recursive because this is a type that was going to have an infinite amount of values associated with it. So if we wanted to define a type for the natural numbers, so these are any positive whole numbers, including 0. Okay, this is a type that would have to have an infinite amount of values. So we couldn't just keep writing that data nat equals 1 or 2 or 3 or 4. We couldn't just keep doing this over and over and over again. We needed some way to specify that, okay, this is how you generate new values of this type. So we used recursion to do this. So another good example of this is if we wanted to redefine the list type that already exists inside Haskell. So to take a look at this, let's recall an example list called list 1. Goes 1, 2, 3. And then we have list 2, okay? If you remember, I pointed this out, this is just special syntax for 1, 2, 3, empty list. Okay? So this is just special syntax for this. We could say that this is the true way to represent a list inside of Haskell. Okay? Now, the interesting thing to note here is that this colon and this empty list here, these can be considered value constructors for the type list. So we could define this in our own way. Let's say we want to define our own list type in Haskell. So we can say type, there's our data, and we'll call this int list. We'll restrict it to being lists of only integers for now. Int list equals, and then what we'll do is instead of having colon here, we'll create a value constructor that would correspond to what colon does in the default list called cons. And the way cons would work is cons would take an int. Okay, so the first part is an int, and the second part is another int list. Okay, so cons takes an int, so it takes an element of the list, and then another list. Or empty. And empty here is going to correspond to these two empty brackets. So the same way that we wrote list2 here, now we could write this in our own custom list. So we'll call this custom list equals cons1, cons2, cons3, empty. Okay, so we've essentially accomplished the same thing. So this is our own list now that we've encoded in our own way using a custom data type that we defined. And if you were to look inside the prelude at how lists are defined, it's roughly defined in the same way, but it uses some special stuff to write colon here instead of cons. Usually you're not allowed to write colon as a value constructor. It needs to be something that begins with an uppercase letter. But just ignoring that fact, you would define lists basically the same way. Okay, where cons here would be this colon, and empty here would be the empty list. Now, the one other thing besides the difference between cons and the colon and empty list and the two square brackets that separated our custom list from the built-in list in Haskell is the fact that the built-in list in Haskell can work over any type, whereas our custom list that we just defined only worked over ints. So to rectify this, we need to use polymorphism. So a polymorphic data type is going to be a data type that takes a type parameter. Okay, so we know this is a type parameter because it begins with a lowercase, and it's kind of attached to the type name here. And it's going to take this type parameter, and this type parameter is essentially, it's like a placeholder for any type. So now this way, instead of specifying specifically that, oh, this was a int list, now it's a list of whatever type A. So if we were to look at how we could redefine this now, instead of writing int list, so let's change the name of it too. Now it'll just be list of A equals, and then instead of putting int here, we put our placeholder A. Okay. And now there's also this is a little bit of extra complication that we need to make note of. Instead of just putting int list here, so first of all, we'll change it to our new name list, but instead of just putting list here, we need to specify, no, it's not just a list, it's a list of A, and we put brackets around it to let it know that this is one thing with cons. If we didn't put brackets around it, then it might look at it being like, oh, cons takes three things. It takes an A, some name list, and another A. No. We put brackets around it to be like cons is attached to two things, A and another list of A. Okay? So now you would notice, so our custom list here, in the same way that we write this as being a list square brackets of integer, now custom list here is a list of integer. Okay, and we could have had another custom list. Let's say a custom list 2, and there's going to be a list of, you guessed it, bool. Okay, so now we've made a polymorphic data type. It's polymorphic just mean it could be many types. Whenever you hear polymorphic, just think of many different types. Now that we're starting to learn more about data types, now is a good time to bring up the case syntax, okay? So we've been using pattern matching already quite a bit in a way that whenever you define the function, you're saying the function, instead of putting a variable for the parameter, we put the actual value and say, well, this is how the function is defined at this value. And then we just write kind of multiple function definitions where we match for each value. Like this. So another alternative syntax for doing this is we write a function like usual and we give a variable for the parameter. And then we write case, the variable we want to pattern match over of, and then we write each different instance. So each value we want to pattern match to. And we use this arrow to specify what we're going to return at that value. So these two functions are defined exactly the same way. And now the case syntax is particularly useful because sometimes you do want to pattern match over a variable, but you don't want to do it inside of the function definition exactly. A good example of this would be, let's say we have our safehead function from before that takes a list and returns the first element of the list, but instead of just crashing, if you give it an empty list, it returns nothing or just the thing in the list if there's one thing. So let's say we have a function first of, and it takes two lists, x's and y's. And what it's going to do is it's going to put those lists together, and it's going to take the first thing from those lists. So we want to use safehead to do this. So we would say x's safehead of x's plus y's. So this way, like let's say x's is the empty list, then instead of returning the first thing of x's, it returns the first thing of y's, right? But if x's and y's are both the empty list, well then it's just going to return nothing, okay? But let's say we don't want this to return maybe a. Let's say we want this to return a and then crash otherwise. So what we're going to want to do is we're going to want to pull out the value from Jess. Okay, we're going to want to pattern match here. So a good way to pattern match without having to find a whole nother function just for pattern matching is we could write the case expressions. We'll say case of, okay? And now we'll write, so what are the two cases here? It's either going to be nothing, and then we'll throw an error, okay? First of two empty lists. Or if it's just x, okay, then we'll return just that x. Let's finish up by talking about pattern matching on lists in particular. So with our new list type, we could have written a pattern match for this by pattern matching on the cons or empty lists. So we could write a function that pattern matches on cons, and it would be cons, the first thing in the list, and the rest of the list, or the empty part. And this is the same in Haskell as writing func x colon x's and func empty list. So to emphasize this, delete this here. Let's write let's rewrite the function map. Okay, let's write our own map. Call it custom map. Okay, so if you remember the map function, it takes a function from A to B, a list of A, and it returns a list of B. So what it's basically going to do is, let's say you have a list of 1, 2, 3, and you want to go through that list and you want to add 1 to everything in that list. What you could write is you could write map 1 plus 1, 2, 3, okay? And this would return the list of 2, 3, 4. Okay, so custom map, it's going to take a function, we'll call it f. So f here is going to be our function from A to B, and some list x's. And what it's going to have to do is it's going to have to move through our list x's and apply the function to every element in the list. So how are we going to do this? So let's start off by pattern matching. So let's start off by just saying, well, how would we apply f the first element of the list? So what we could do is we could pattern match and be like, well, instead of just putting x's here, we'll have the list x colon x's. So now x would be the first thing of the list. Okay, so in our example here, remember this list 1, 2, 3, this is the same thing as writing 1 colon 2 colon 3 colon empty list. So when we write this pattern match x colon x's, x is 1 here, and 2 colon 3 colon empty list is x's here. So x's is a whole list, and x is just one element of the list. So to start off, what we're going to do is if we want to just apply f to the first thing in the list, we're just going to apply f of x. And there we go. Now, the trick here is now we have to move through the list x's and apply f to every element in that list x's. So we need a function now that takes f and applies it to everything in the list x's. But of course, that's what we're doing right now. That's the function we're making at the moment. So what we're going to do is we're going to have custom map f of x's. So we're just going to call the function again on the rest of the list x's. And now what we need is some way to put this together with the rest of this list. So what's happening is this is going to be one element now. Let's put this, we don't have to put this in brackets, but let's put this in brackets just to be super clear of what's going on. So f of x is going to be one element, and custom map f x's is going to be the rest of the elements. So how do we put these together? Well, that's exactly what this colon does. This colon takes one element and another list, and it puts them all together into one list. So we're just going to put a colon here, and we can put this all on one line. Okay. So now this is the recursive case, okay, that we have going on right now. What else do we need? So right now, this will go on forever. Well, actually what it'll do is this will keep going until this pattern doesn't match anymore. When does this pattern not match anymore? When you get to the empty list. So eventually you get to the empty list, and then you can no longer match it to this pattern x colon x's. When you have the empty list, like say the empty list right here, eventually x's becomes the empty list here. Like when you get to 3 colon empty list and you pattern match to this, then x's will be the empty list here. And then there's no colon anymore. Nothing to pattern match there. So what we need is a case now of f empty list. Okay, so this will be our base case, we would call it. And what do we return in the base case? So let's kind of like walk this through. Like if we were to evaluate this, let's say we're going to call custom map 1 plus 1 colon 2 empty list. So it's just a list of 1, 2. So what does this get evaluated to? Let's move through it one step at a time. So we're going to sub this in. So 1 colon 2 colon empty list is going to pattern match to this, where x is 1 and 2 colon empty list is x's. So we're going to have 1 plus 1 colon custom map f2 colon empty list. Okay. So now we need to, let's forget about this part for the moment. Now we need to do the same thing, but on this part here. So what does this match to? So custom map is going to match to, let's say 2:empty list is going to match to x:(x) here. So now this is going to be 1 plus 1 colon brackets. So now this time f of x, so 2 is going to be x here. So this is going to match 1 plus 2 colon custom map, it's going to be called again f, and now x is here is going to be the empty list. So the empty list here. So now we need to decide, all right, what should this evaluate to finish up this list? Well, whenever we have a list like this where it's like 1 colon 2 colon whatever, what does it always end up ending with? The empty list. So when we get to the empty list, we should just return the empty list. Okay, and now that'll finish this evaluation. 1 plus 1 colon 1 plus 2 colon empty list. So 4 will turn into 2 colon 3 colon empty list, which is just another way of writing the list of 2, 3. So this pattern here of moving through lists, whenever you want to move through a list and do something one at a time on that list, you can always use this pattern of matching on x:(x's, doing your thing, making a recursive call on the tail x's here, right, on the rest of the list, and then just keep going until you get to the empty list. So this is a pattern we use all the time when writing algorithms on lists. So we'll stop here for now, guys. I hope you're enjoying learning about data types, what you've learned so far about them. You're going to see that they're very, very important to not just programming in Haskell, but programming in general and computer science in general. Till next time, guys.